we had a few problems with the circuit and the software, which leads going to its drain now.
We put a bit of a capacitor filter on it. We just guessed, pulled a value out of the air. However, it does cause about a 5 microsecond delay, and I'm not 100% sure if we need it. If we do, we'll revisit it in the future. But if you look here, the magenta is the waveform coming in, and there we go, about a 5 microsecond delay. So I've removed the capacitor now, and I'll just try again. And now you can see, in fact, at the bottom of the pulse there's very little delay, and the top of the pulse is very little delay. So the delay is the same on each edge, is what we want really. So that means then the pulse width being measured is approximately the same as that coming in. So in the filter circuit we removed the capacitor. Also, we realised that the input side of the optocoupler had an LED one direction and nothing in the other direction. So we've put an LED in the other direction across the optocoupler. And so there's a similar load each way, and it saves the LED inside having a lot of reverse voltage across it. So that's the two main circuit changes we've made. And we'll just let it evolve as time goes by. So we made some changes to the circuit associated with decoding the signal in the hardware. First of all, we put a diode across here just so it complements the diode in there. So the reverse voltage across the diode within the chip is reduced. It also gives a nice indication that we're actually getting a signal. The other thing is this capacitor. It was allowing the signal to be skewed because this is an open collector output. This didn't filter on every edge. It only caused filtering on when this transistor was switched off. So we removed that. So we just removed that now. However, what we found, we're still getting odd triggering and pulses coming in here. And if you look at this following picture of the scope, you can see there's lots of ringing on it. And then after that, there's a picture here of the actual circuit, and you can see on the bottom left hand corner there's two inductors on the output, and we guess this is to make it CE electromagnetic compatibility compliant, and hence ringing. But what it was causing mistriggers. And what we found, there was very short pulses here that would shorten the pulse width count. And that's why we originally put the capacitor across there, but of course it's making problems in its own right. So we changed the value of this resistor, and we tried 7 ohms into that position, and it worked. And it's all to do with the capacity within this unit. The original reason for this was when this transistor switched off here, it would discharge the output transistor here, and that would give a better edge to the pulses. So that seems to work. We haven't calculated anything. Maybe on the edge, may need changing in the future.
We are now going to explain the academic of the
Okay, if we look at the signals we've got on the scope, what the software looked for is a minimum of 14 1 bits, which is the preamble. And when we detect that, followed by a 0 bit, we know that's the start of the packet and the first data byte here. A 0 in this position here tells me it's an advanced function and refers to the speed and functions of the train being addressed. If that was a 1, that would have other functions which we'll go to look into at a later time. In this case then, as it's a 0, we have a range of 01 to 127 train addresses, so it can be between that range. Then we get a 0 bit, which is the beginning of the second data byte. And then in the most significant bit here, a 0 in this position tells me the train speed step value followed by the train speed and direction byte. So this is the step value, and this is going to be followed by this byte here, which is the speed and direction byte. So we have step value of 126, and as I said in the video, this here limits the top speed of the train. Then we get a 0 start on the third byte, and here we got a 0 in the most significant position. Tells me that train is being commanded to go in reverse. If that was a 1, it'd be forward. Then we have 127 speeds here from 0, where there's all 0 bits, and here is the maximum speed, where there's all 1 bits. Then after that, we get the next start bit of the fourth data byte. Now this data byte is a cyclic redundancy check byte, which is an exclusive OR of the previous data bytes. So exclusive OR of that, of that, of that gives us a result. So the command station sends that result, and if we calculate the result to be the same, we know then that the data packet has not been corrupted by railway noise, the wheels on the rails, and it's correct. And at the end of this particular packet of data here, instead of a 0, we have a 1, and a 1 bit tells us that's the end of the packet.
We are now going to break it down. Here's the operation.
So this is where we define the variables we use in the interrupt routine. These are defined by the code configurator, so we're not using them directly, maybe indirectly. Then what we have here is the variables we set up. The preamble is a counter we use to count up the number of consecutive ones. When we get to 12, we know we've probably got a preamble number of bytes. So from then on, when we get a 0 after that, we know that's the start of a data byte and the start of a data packet. Scope sync is our sort of state machine. We use the switch statement in C. So when we come into the program, depending on what task we have to do in the steps of building up the data packet, that will point to which piece of program we should run every time we come in. So for instance, when it's 0, it will just clear everything down, set everything up. Then in that first state, if it sees a 1, it goes on to the next program, that becomes 1, and it ignores the first program, goes on the next program in the switch statement, which then starts reading and looking for the preamble ones, and so forth. It builds up. The bit counter, that is basically, as we build up each bit, we put them into a register, well, we put it into the data packet buffer, and that basically, then we shift it left 1, and then we put into bit 0, and then we shift left 1. So we build up 8 bits are built up, which makes a byte. So once we get to 8, we know that we've got a byte of data. This min and max, these are the values in the counter that come in. That's a 1 if it's between 2 and 260, and 0 can be 360 right up to 40,000. The 40,000 represents over 16, no, it's 10 milliseconds. The 0 can be stretched by 10 milliseconds by the controller. So we forgot that, to be aware of that. So as I said, the packet buffer, the bottom 5 bytes are built up, and once the packet's been received and decoded, we then shift it using a for loop with this into the top 5 bytes, and then we signal to the main program that the packet's complete. The reason we do that is that if the main program takes time to read all the data, it's possible that this interrupt will overwrite what's in the data. By making sure it only writes to the lower 5 and the main program only reads the upper 5, there'll be no risk of that. Okay, so we come in here when we get an interrupt. The first thing we do is we clear the interrupt flag for timer 1. We then read the value of timer 1 into this period value. Then we clear timer 1, and then we start off priming timer 1 for the next pulse that may come along. And if timer 1's overflowed, this data is corrupt. So we actually clear the overflow flag on timer 1, and we then make scope sync 1, which when we go down to here, scope sync 0. So when we come down to here, this start of packet acquisition. So it just resets everything, and it keeps coming through here until it receives a period value of a 1. Then it makes a scope sync equal 1. So the next time it comes through on an interrupt, it'll go to case 2, or case 1, sorry. Here, if the period value is a 1, it will increment the preamble counter. If the preamble counter is equal to greater than 12, and we've just received a 0, that means that is the start bit of our first byte. So we then go on to the next program, which is decoding the next byte, which would be case 2. If the preamble counter is equal to less than 11, and the period value is greater than the 0 minimum, then the scope sync is set to 0, which means we go back to the beginning and start all over again, because that is not a valid preamble. So we've now got a preamble, and we've got our 0 bit, which is the start bit of our first byte. So we just got to shift left our packet buffer contents. If the period is a 1, then we're going to OR it with bit 0. Then we're going to increment the bit counter. If the bit counter is equal to great, then we go on to the next state. If not, and we'll clear the bit counter, and we'll increment the buffer offset. This buffer offset means here starts at 0, and as each byte is built up, this gets incremented so it fills up the lower half of the buffer. If we didn't, if the bit counter isn't equal to greater than 8, then it just comes back through and does the next bit, filling up that byte. Okay, so when we get to case 3, we've got a byte of data. It says if the period value is a 0, scope sync 2. So it's the start of the second byte. So we then take the second byte in. Else, it means this is a 1. it means we're going to go back to the beginning, but it means we've got a valid data byte because a 1 is the end of the data packet. If packet complete is 0, that means the main program will read the packet complete, and it will make it 0 if it's completed its operation. But if we got a packet and it is 0, we can then set it to 1 to tell the main program that we've got a valid packet. Okay, valid packet equals buffer offset. This is to tell the main program how many bytes or how big the data packet is, because you can have just simple functions, or you can have speed, so you can have different lengths of packet. So this tells the main program how big the packet is. Okay, this is where we shift up using a for loop up to the top 5 bytes of our packet buffer. Right, if byte offset is less than 2, or the packet buffer 0 is greater than 0.2, and then we just make packet buffer complete 0. What we're doing, we're just filtering out, for instance, packet buffer. If it's greater than 2, we're doing all the trains, otherwise we're going to be overloaded. So this does train, this does the 0 address and the 1 address for train 1. If not, it just starts again. If the buffer offset is equal to less than 2, that means that we haven't built up a whole packet of data. It's only 2 bytes of in the packet buffer, which isn't a valid data byte. So once again, reset. And that is how the interrupt works. So the variables used in the main program here, that packet buffer was generated in the interrupt routine, so was the packet buffer complete. So to use them in the main program, we have to tell the compiler that the external definitions for these variables, so that it'll look elsewhere for them, so then we can still use them in the main program. Exclusive OR result, this is what we build. We work out with exclusive OR all the data bytes, and then the result, if it equals the transmitted exclusive OR CRC byte, then we know we've got a valid piece of data, and that's what it is. Valid piece of data says, yep, it's valid, we can go ahead and run that. System initialize, that was generated by the MCC interrupt enabled, so we now know that we can get interrupts. The peripheral interrupts enabled, and then we start off the single pulse acquisition. This is a function generated by the MCC, so now everything starts running and it'll start capturing pulses. Okay, so if packet complete is 1, then we know that the interrupt program has filled up the top 5 bytes of the packet buffer with the data it's received and built up. I'm just switching the LED on for my own use. There's an LED on that port, so it switches on, so we know we're in this piece of program. If packet buffer is 03, that's the buffer size. That's the packet size, sorry. So if the packet's 3, we know that we've got address, data, and cyclic redundancy check, number of bytes. So we get an XOR result by packet buffer 5, packet buffer 6, which is the address and data, and the result there. If the result we generated equals the result of the packet buffer 7, which is the transmitted CRC, then we know we've got a valid piece of data. Else, now this is where we assume that it's not 3, it's 4. So we've got 4 bytes of data. So therefore we got exclusive OR these sorry, we've got 4 bytes of data because it's exclusive for all these 3 bytes together, which is address, data, data, and then we compare that with the result. And once again, if it's a valid packet buffer value, then it's a valid data, so we can transmit it. So as valid data, we print out the address, data byte 1. If packet buffer 9 is 03, then and a valid data, then we print out data byte 2 as a blank, because there's no data for data byte 2. And then we print the transmitted CRC, and then we print our generated CRC. However, if it's 4 bytes of data, including the CRC, then we print out data byte 2 and then the 2 CRC values. Then we make packet complete 0, so it tells the interrupt program that they can now start building the next lot of packet of data. We make valid data 0 because we set it above and we finished with it. And then we switch the LED off, so we know that we've ended this piece of the program. And that's the main program.
And now this video, we are going to review our